So I want to welcome you back to the last part of this tutorial on 4 decades of array signal processing research and optimization relaxation techniques perspective. We will first discuss successive approximation techniques in this last part that can be used as efficient optimization strategy for computing the extrema of multimodal, multidimensional objective functions for multi-source direction of arrival estimation. We will in particular look at the class of majorization-minimization algorithms where the original cost function is successively approximated by upper bound functions. In this class of approximation techniques, we will study the popular expectation-maximization algorithms, or short EM algorithm. After this, we will discuss theoretical performance bounds of methods developed under the partial manifold relaxation framework, and we will introduce closed-form Kramer-Rao bound expressions in this last part of this tutorial that reveal some very interesting properties of the methods developed under the partial relaxation framework. But they will also reveal some new properties of existing subspace estimation methods, in particular the music method. Let us briefly recapture. We have observed that the multi-source criteria show excellent threshold and also asymptotic estimation performance. However, this comes at the expense of a high computational cost, as they require exhaustive multidimensional search. And this search is prohibitive if the number of sources exceeds values such as n equal to 3. Instead of the multidimensional optimization, we can employ approximation techniques such as alternating projection or block coordinate descent, which are viable options for local convergence. The majorization-minimization approach is an iterative optimization technique where the original optimization problem is approximated by a sequence of upper bound problems. The idea is that the approximate upper bound problems are designed in a way that they are much easier to solve, potentially in closed form, than the original problem. This is illustrated in the figure over here. Given a multimodal objective function, such as the likelihood function L of x that depends on the parameter vector alpha, and that we want to minimize with respect to alpha. Instead of directly minimizing the function, which is difficult, we minimize the sequence of approximate problems. These approximate problems are obtained by local upper bound approximation. At iteration k of the successive approximation procedure, we approximate the original function L of x given alpha at some given point alpha hat k. And we approximate it by an upper bound function that is denoted by L bar of x and alpha. Then we minimize the upper bound function instead of the original function. The minimum is given by what we denote as hat or alpha k plus 1 hat. In the next iteration, we continue by approximating the function at the current point, and that is alpha k plus 1 hat. The approximate function should be chosen in such a way that the approximate problem is much easier to minimize than the original problem. Applying this procedure to the maximum likelihood estimation problem, we want to minimize the likelihood function L of x given alpha with parameter vector alpha in the following. At iteration k, we minimize the approximate function lambda x bar which is an approximation of the likelihood function at point alpha k hat. In order to guarantee convergence, the approximate function must satisfy certain regularity conditions that were already mentioned by my colleague Minh Trinh-Hoang. First, the upper bound property must hold. Hence, the graph of the approximate function must be strictly above the graph of the likelihood function. Second, the approximation must be tied at the current point given by alpha k hat. The expectation-maximization algorithm is a special case of the majorization-minimization algorithm. The idea is to introduce additional variables, the so-called unobserved data vector, y, that cannot be observed directly, but that is related with the observed data through a simple mapping x equal to t of y. Hence, given the unobserved data, the observed data is fully determined. The reverse statement generally, however, does not apply. The vector y and the vector x together form the complete data. Let f of x given y with parameter alpha denote the conditional probability density function of the observations x given the unobserved data y with parameterization alpha. Similarly, let f of y with parameter vector alpha be the probability density function of the unobserved data y. Then we can use Jensen's inequality to find an upper bound approximation of the log likelihood function L of x given alpha, and the likelihood function can be written as a conditional expectation of the ratio function given over here, where expectation is taken with respect to the random variable y, so the unobserved data, conditioned on x and alpha k hat. The ratio function is represented by the joint PDF of x and y given alpha divided by the conditional PDF of y given x and alpha hat k, where alpha hat k is the current estimate. Now with Jensen's inequality we obtain that the negative logarithm of the average is smaller or equal to the average of the negative logarithm. After again employing Bayes' rule, we obtain that the result can be expressed as a negative of the conditional expectation of y given x and alpha hat at iteration k of the logarithm of the PDF of y given alpha plus some constant terms that do not depend on alpha and that we omitted. This function can be considered as our approximate function L bar at iteration k, where the approximation is taken at the point alpha hat k. Next, we apply the expectation-maximization algorithm to the example of the deterministic maximum likelihood signal model, where we assume that noise variance nu is known. In this example, it is convenient to define the unobserved data as the signal contributions of the individual sources that we add up in the observed data. So we define a vector yn as the product of the n steering vector A of theta n multiplied with the nth waveform Sn, and where we also add n of t, which is modeling the contribution of the noise. The contributions of all sources are then concatenated in the vector y. These individual signal contributions cannot be observed directly, and only their mixture, that is the superposition, is observed. In other words, x of t is the sum of all unobserved data components yn of t, with all n going from 1 to capital N, so the number of signals. So as I said, note that also in the signal contributions we are modeling part of the noise in each unobserved data as Nn of t. The sum of all individual noise contributions add up to the noise vector n of t of the original model. The same applies to the noise variances. With this definition of the unobserved data y, the approximate, that means upper bound, cost function at point alpha k hat is given by the sum of square functions, where each square function only contains the parameters of a single source. That means that the problem is separable in the different source variables, and we can estimate the parameters of each source independently and in parallel. In each summand of the cost functions, the first terms are constant and depend on the observed data and the current estimates. This part can be understood as the residuals of the received observed data after subtracting the current value of the interfering sources at iteration k. That means we are subtracting all sources except for the n source. The second part contains the variables for the model of a single source, that is, the n source that we want to estimate. The computation of the approximate function is generally termed the expectation step of the expectation-maximization algorithm. In the next step, the maximization is performed. So the maximization step follows. The maximum of each summand function is a simple optimization problem that we can solve in parallel, and the solution of each subproblem is given by the conventional beamformer that is also known in a different context as the matched filter. That means all subproblems are solved in parallel, and they are easy to solve, and we obtain the estimates of the k plus first iteration of the EM algorithm from it. Next, we turn our attention to the performance assessment of the estimators by taking a look at conventional performance bounds. So we will start with the conventional Kramer-Rao bound for the deterministic and the stochastic signal model, before we turn our attention to newly developed Kramer-Rao bounds that reveal some interesting properties for the partially relaxed signal model. Let us assume that we observe the stationary random process x with observations xt for time instances t ranging from 1 to capital T. We assume a non-redundant deterministic real-valued parameterization characterized by the parameter vector alpha. The probability density function corresponding to the stationary random process is denoted by f sub x of x, given the parameter vector alpha. For simplicity, we assume that the observations are independent, identically distributed. The objective is to estimate the parameter vector alpha true, so the exact parameter vector, from the observation x1 to xt. Using the help of an estimator, alpha hat, which represents some mapping or function of the observations. Let this mapping of the random observation be denoted by t of x1 to xt, and let mu, vector mu, and matrix sigma denote the mean and the covariance matrix of the estimator. Then the Fisher information matrix, short FIM, is defined as a negative of the expectation of the Hessian taken with respect to the parameter vector alpha of the log likelihood function given over here. The log likelihood function, as we mentioned before, is obtained by taking the logarithm of the PDF after inserting the IID random observations. A fundamental result in estimation theory states that the covariance matrix of any unbiased estimator, alpha hat, is lower bounded by the inverse of the Fisher information matrix, which is determined as a Kramer-Rao lower bound matrix. For the special case of circularly symmetric complex Gaussian random observations with mean given by the vector m, which is a function of the parameter vector alpha, and the covariance matrix given by the matrix K, which is also a function of the parameter vector alpha, the Fisher information matrix can be easily computed using the well-known Slepian-Banks formula. This formula is given over here, and it only involves the partial derivatives of the mean and the covariance matrix with respect to the parameter vector alpha. For the Kramer-Rao bound, that means the inverse of the Fisher information matrix, to exist, the parameter vector needs to be identifiable from the observations, at least locally around the true parameters. A necessary but not sufficient condition is that the parameterization is non-redundant. That means for different parameters or different parameter vectors do not create the same observations in the noise-free case. Often we are interested only in part of the variables and consider the remaining parameters as nuisance parameters. For example, in the context of DOA estimation, we are interested in the directions of arrival of the impinging sources, while the other signal parameters such as the noise variance, the signal waveform, or the signal covariance matrix are considered as nuisance parameters. Let us partition parameter vector alpha in two parts: the desired part containing the parameters of interest and denoted by theta, and the nuisance part containing the remaining parameters that are of no interest. Correspondingly, we can partition the Fisher information matrix as well as the inverse of the Kramer-Rao lower bound matrix in the same way. In this partitioning, the upper left block, denoted by C of theta theta, is of particular interest as it represents the lower bound matrix of the covariance matrix of the estimates of the parameters of interest. Using the block matrix inversion formula, we can obtain the following compact expression for the Kramer-Rao lower bound matrix. This is a Kramer-Rao lower bound for the general complex Gaussian model. Now, let us apply this result to our deterministic and stochastic signal model introduced in the first part of the tutorial. In the deterministic case, the observations are complex circular Gaussian with mean A times S and covariance nu times identity for all time instances from t equal to 1 to t equal to t. Making use of the Sleep and Banks formula and the block matrix inversion lemma, the deterministic Kramer-Rao bound of the DOA parameters of interest is then given by the compact closed form expression over here, where P hat is a sample correlation matrix computed from the exact signal waveform, and D is the matrix of partial derivatives of the steering vector at the true source locations where the differentiation is carried out with respect to the directions of arrival. Pi perp is a projector onto the orthogonal complement to the space spanned by the steering matrix for the true source direction. That is the orthogonal projector onto the noise subspace. Next, we consider the stochastic signal model, where observations are complex circular Gaussian with zero mean and covariance matrix given by A, P, A Hermitian plus nu times the identity matrix. The stochastic Kramer-Rao bound of the DOA parameters of interest is given by the closed form expression over here, which is similar to the previous formula, with the main difference that instead of the signal correlation matrix P, the matrix M is defined over here on the left side is used. The true Kramer-Rao bound expression, the deterministic and the stochastic Kramer-Rao bound, can be easily computed, and they can be used as benchmarks for the performance evaluation of any unbiased estimator. So if you have an estimator that is close to the Kramer-Rao bound, you know that you cannot improve it much. Let us now return our attention to the algorithms developed under the partial relaxation framework, the partial relaxation of the interference structure. Recall that we define a relaxed n-source array manifold as a set of all full-rank m times n matrices A, with the first column belonging to a given single-source array manifold and the remaining n-1 columns relaxed to an arbitrary complex matrix of dimensions m times n-1. The measurements generated under the partial relaxation model are obviously different from the signals generated under the conventional signal model, as the observations are generated with different prior information of the array manifold. From an estimation theoretic perspective, in this context, some interesting questions arise regarding the fundamental limits of the estimation performance of the estimates developed under the partial relaxation framework and its relation to the conventional stochastical signal model, for example. Intuitively, the relaxation of the interference part of the manifold matrix is associated with an information loss. However, we are interested in characterizing this performance loss and gaining further insights whether the performance loss induced by the relaxation is unavoidable or not. To answer this question, we derive the Kramer-Rao lower bound for the DOA parameters under the relaxed signal model. We refer to this bound as the partial relaxation short PR Kramer-Rao bound, so PR-CRB in the following. The PR-CRB is the lower bound for all estimators derived under the partial relaxation framework that we considered in the second part of this tutorial. In this tutorial, we consider the stochastic signal model and derive the corresponding stochastic PR-CRB. In this case, the covariance matrix is a sufficient statistic for the parameter estimation. Hence, we study the representation of the covariance matrix in the stochastic model for the partial relaxation model. In order to satisfy the necessary condition for the invertibility of the Fisher information matrix, and therefore the existence of the Kramer-Rao bound, we need a non-redundant parameterization of the transmit covariance matrix P, as well as the steering matrix A under the partial relaxation model. It is easy to see that the parameterization that we use in the derivation of the partial relaxation algorithms, that is the model of the unstructured interference, this parameterization is highly redundant as the number of parameters largely exceeds the number of equations in this covariant model. Yeah? So if we count the number of equations over here. To obtain a non-redundant representation, we therefore introduce an alternative parameterization indicated by the overbar and the structures that we illustrate here, where we restrict part of the entries in the steering matrix to 0, for example, the first row of the matrix, or to an identity matrix that is here the lower part as indicated. And we only leave n minus n times n minus 1 parameter free. And this corresponds to the number of complex equations that we have to represent the covariance matrix. This representation ensures the invertibility of the PR Fisher information matrix. The stochastic Kramer-Rao bound for the PR model is then given by the closed form expression over here. Comparing this bound to the stochastic Kramer-Rao bound of the conventional model given above, we observe some similarities. Both Kramer-Rao bounds depend on the matrix M defined here on the left side, as well as the orthogonal projector onto the noise subspace and the derivatives of the steering vectors at the true source locations. The main difference is that the Kramer-Rao bound, the PR Kramer-Rao bound, is a scalar quantity that only refers to one particular source DOA, that is the source of interest. The closed form expression of the PR Kramer-Rao bound given over here allows us to provide an analytic comparison between the stochastic Kramer-Rao bound with a conventional stochastic Kramer-Rao bound, and this allows us to draw some interesting conclusions regarding the asymptotic estimation performance of some known DO estimators in the literature. The first result that we show confirms our intuition that the partial relaxation Kramer-Rao bound for the DO estimators of a particular source n is always lower bounded by the corresponding Kramer-Rao bound of the conventional model. Hence, a performance loss associated with a partial relaxation approach is generally unavoidable. However, we can analytically show that in the high SNR regime and for uncorrelated sources, this performance loss is negligible. And in this case, the use of the partial relaxation approach can reduce the computational complexity of the minimization without sacrificing the performance. We can also show that two of the estimators, namely the partial relaxation deterministic maximum likelihood estimator and the partial relaxation weighted subspace fitting estimator, derived in part 2 of the tutorial and provided over here, can asymptotically for large sample size achieve the Kramer-Rao lower bound. Hence, they are asymptotically efficient for parameter estimation under the partial relaxation model. This result holds true irrespectively of the choice of the positive definite weighting matrix W in the partial relaxation weighted subspace fitting criterion. This result is somehow surprising, as we know that in the conventional model, the choice of the weighting matrix in the weighted subspace fitting criterion is of critical importance for the asymptotic performance, and this property has been used to devise optimal strategies for the choice of the weighting matrix. For the PR weighted subspace fitting algorithm, this is not the case. The asymptotic performance of all positive definite weighting matrices is identical. This also means that the asymptotic performance of the PRDML, the PR weighted subspace fitting, and music, which we showed corresponds to the PR weighted subspace fitting with identity weighting. All these methods are identically in the asymptotic regime, and the performance is characterized by the PR Kramer-Rao bound that we derived. We remark that even though the asymptotic for large T performance of all these estimators is identical, the performance in the non-asymptotic regime and in the threshold region can be quite different, as we saw in the simulation results of part 2. This brings us to the end of the tutorial. So let us summarize. In this tutorial, we provided a broad overview of existing direction of arrival estimators developed in the past 4 decades. The history of the development of new DOA estimation methods and the development of efficient convex optimization strategies have always been closely interrelated and have affected each other. We have revisited these estimators from a modern optimization techniques perspective, using the concepts of convex approximation and convex relaxation. With respect to the relaxation, we showed that deliberately ignoring part of the problem structure and therefore prior information can drastically reduce the computational complexity associated with the estimation task without necessarily sacrificing significantly in the performance. We consider different types of relaxation, namely partial relaxation of the array geometry, as for example in the ESPRIT and the REA algorithm, and the partial relaxation of the interference structure, as for example in the PR estimators. We hope that the new partial relaxation framework and the approximation methods that we introduced in this tutorial inspire you to design your own partial relaxation and approximation algorithms by revisiting existing estimation approaches for more advanced data models in the context of direction of arrival estimation and also in other applications. Furthermore, we encourage you to apply the relaxation approach also in the theoretical performance analysis to better understand which particular prior information is implicitly relaxed in specific low-cost algorithms that you want to analyze. Let me end by remarking that the MATLAB code for the efficient implementation of the partial relaxation algorithms is available in this GitHub repository, and I invite you to download it. Finally, I append some references here, and I thank you for attending this tutorial. I hope you enjoyed it.